Green screen, so I'll start this. I didn't have news prepped for today because I have a news segment coming that I need to read some more about. And then the universe provided me with some Bitcoin news. So I have to move this down a little bit. Oh, well, you know what? We'll just scroll. So for a period today, a lot of people using Bitcoin basically couldn't access their wallets, so like any of their money. And it seems like this is because of, you can see here in the middle, a fire in a data center that caused an outage. And so there's a lot of interesting things to think about here. I didn't prep a slide because this happened like very, very much right before lecture. But it's interesting to think about both how we design systems that should be, robust to failure and sort of robust to these types of failures, like a fire. I mean, that can easily take out an entire data center. What do you do about that, if anything? But also to think about, like when a system like Bitcoin, that's not the great way to say it, but like when something affecting Bitcoin is down, people can't access their money, right? And so like, how does that help us think about the types of incidents we provision for? So we'll actually talk about this type of reliability when we get to later in the class, but that's today's news. It seems that they're solving the core issues. This page seems to update automatically, so we'll see what happens. We'll see what has happened by the end of class. All right, so we're going to wrap up operating systems today. You have seen quite a few things about operating systems. You've solved all of these problems, right? And we've seen things like virtual memory, system calls, bounded buffers, locks, threads, all of these things. What we're going to talk about today, we're going to talk about a few things. At the outset, they're going to seem a little bit unrelated, but I promise that there is a narrative thread here. One of the things we're going to talk about, the first thing we're going to start with, is another application of virtualization. And in particular, we're going to talk about running multiple operating systems at once on one machine. A little bit about why we might do that, a little bit how we might get that to work. But this is going to be another application of virtualization. From there, we're also going to talk about the structure of the kernel itself, right? What is modularity like inside of the kernel? We've sort of focused on the role of the kernel in relation to user programs, but like what does the kernel look like? What is that code base like? And then we're also going to talk about some performance issues, right? So again, I know that this might seem, when I put it as a list, as like miscellaneous topics that we're just trying to wrap up, but they all have a theme. All right, so let's talk about this first problem. Okay, it is common today to run multiple operating systems on a physical machine. And there are a couple of different reasons you might do this, but I'll show you. I have this up on my machine. So sometimes users just might need access to another operating system. So my laptop, which you all have never seen because we're virtual, my laptop is a Mac laptop, but sometimes I need access to Linux. So what I have here is Linux not running in a virtual machine. I would not like to upgrade it. It'll come back. Give VMware a second. But I can run Linux in what is called a virtual machine, which means I have access to basically a full Linux desktop on my laptop, although hilariously, apparently sharing it in Zoom causes it to just die. So we're going to come back to this in a second while I watch it reboot itself. And so that is one way. Some of you may have done that. Some of you may not have done that. You can hear it start if you can still hear the sound on my computer. Kind of fun. Another place we might use this is in a data center, right? To call back to our Bitcoin news item from earlier. So you can see here, see if I can drag it. There we go. So here's an Ubuntu desktop running on my laptop. This is an old version of Ubuntu. We'll talk about why that is later on. Right, but I can do all sorts of things, right? I have a terminal. It's just normal Linux running on my Mac laptop, right? Again, another place you might do this is on a data center, right? If we have multiple users sort of, or multiple jobs running in a data center, one of the ways they might run is on multiple instances of an operating system, just on one physical machine, right? So because this is so common today, and because you know so much about virtualization, this is an interesting thing to think about, right? How would this work, right? There are a couple of things we need to deal with. How do we share access to a single physical machine across multiple operating systems, right? Like I'm running Mac OS and I'm running Linux, right? Do they each get access to the full physical hardware? How does that work, right? And then how do we protect them from one another, right? This is a particular concern, if you're thinking about a data center where maybe the operating systems running alongside of yours are actually malicious, or maybe you're just even worried about like, well, what if there's a bug in Linux, all right? And I don't want it to crash the other operating system, all right? Now, these questions should be familiar, right? Because they're the same questions we asked when we tried to figure out how to enforce modularity on a single machine, right? We asked, okay, well, how do I share the hardware between multiple programs? How do I protect programs from one another, right? Here, we're kind of zooming out one level, right? How do I share the hardware between multiple operating systems? How do I protect operating systems from one another, all right? So we're going to think, we're gonna think about the things that are the same here and the things that are gonna need to be different, right? So first of all, though, you should at least go into this believing me that things can indeed work this way. So we're going to do an interesting demo. Always an exciting demo for me because I never know what's going to happen in this demo. All right, so here you see I'm dragging you back Linux here. And one of the things that we would like to have happen if all of this is working, if I introduce a bug into this operating system, what we would like to see is, well, maybe Linux crashes in this virtual machine, right? But I would like the rest of my operating system to survive, all right? So we're actually gonna test this. So what I'm gonna do, I'm gonna install basically a small kernel module. So I'm gonna install some code into the kernel, and it's just gonna randomly choose locations in physical memory and write a random byte to that location, right? This is in general not something you wanna do. You don't just wanna like overwrite memory randomly. That's a bad idea. But we're gonna do it in 603T. That should be fine. Okay, so this is running. You can see I'm looking at basically some messages from the system. It's corrupting memory locations. It doubles the amount that it corrupts every so often. We're just going to keep watching this for a while. Sometimes it ends really quickly. Sometimes it takes a really long time to end. Sometimes it fails in spectacular ways. Sometimes it fails in very quiet ways. But you can see here it's failed in somewhat of a quiet way. So I've run this dmessage command, which again is getting these messages from the operating system. And just sort of now nothing is really happening, right? I can't really interact with this virtual machine anymore. In fact, it's captured my mouse. So that'll be a fun thing for all of us to deal with. But as you can see, the rest of my operating system here is working okay, right? I'm still talking to you, okay? If the whole thing had failed, that would have been a bad time for us, right? Lecture would have ended. Now, this probably is not exactly what I expected to happen because I did expect to be able to still have access to my mouse. Here we go. Imagine if the whole lecture was just you all staring at that screen. Fun times. All right, so I'll bring that back for you if it reboots. Sometimes it reboots in an interesting way. Sometimes it just sits like this. All right, but this is a good thing. It's a good thing for you that the lecture continued. It's a good thing for me that I got my mouse back. And this is what we want to happen. I want that virtual machine to be able to fail and everything else to keep going. Okay, so how did this work? Right, this is what we're going to talk about today. How did we get this to happen? So first of all, there are two common ways to do this. All right, this is what you saw me do, this picture here. All right, I had a host operating system, it's Mac OS, sort of the default operating system on my machine. And I ran Linux inside of it as a guest operating system. All right, on my machine, like to my Mac OS, to the file system, the Linux VM just looks like a bunch of files on a disk. The VM is basically running just as another process. All right, it's a full-fledged operating system, so there's all sorts of interesting things happening. In fact, when I plugged my iPad in to start this lecture, it let me connect it to both the VM and to the regular operating system. So all sorts of interesting things going on. All right, but to illuminate the issues of how virtual machines work and sort of how they relate to the operating system stuff you've seen so far, we're going to look at a slightly different model. All right, instead of this notion of having a host operating system with a guest operating system inside of it, we're going to think about multiple operating systems running alongside each other. All right. The details are very, very similar in either case. I think this one has nicer parallels with what you've seen in this class already. This is also more of what you would be thinking about if you were saying renting a machine in a data center, right? Your operating system is one of these, maybe my operating system is one of these, something like that. All right. So in getting this to work, we have one interesting thing to think about that we didn't really have to think about before. All right. We didn't really have to think about when we were talking about operating systems just on their own. One of our big constraints here is compatibility, right? I want to be able to run, say, on my laptop, like the existing Linux kernel. I don't want to have to change it to get it to work on my machine. I just want to run it as is. And so this means that we can't just say like add new operating system abstractions into Linux, right? We're gonna have to make do just with virtualization. All right, so our main issue here is gonna be just like it was with the rest of operating systems. How are we gonna safely share the hardware? All right, so let's think of the whole spectrum of possibilities here and where they might fail. All right, the first thing I could imagine doing, just take both of these operating systems, let them run in kernel mode when they need to, let them talk directly to the hardware, just like they normally would. All right. This is going to fail, right? This is not the enforced modularity that we worked. For instance, if one of these kernels has a bug, it's potentially going to cause the others to fail. They would both have access to memory. This is just not what we want. All right. So that's one kind of point on the spectrum. So just, for fun, let's imagine the other point in the spectrum. Right? What if we tried thinking about, letting them kind of run in user mode, that's a little bit confusing to talk about. We don't really talk about like running a kernel in user mode, but like let's just go with this. Because if you're running things in user mode, there are a lot of things that actually go just fine. Right? There are a lot of instructions that don't require any sort of special privilege. Right? There are a lot of just user level instructions, adding, subtracting, multiplying, all of that. All of that would work fine. But of course, the place where we're going to get the problem is, when the kernel needs to kick in, right? When either of these guest operating systems need to do something that's privileged, right? They won't be able to access any of those privileged instructions. These operating systems are assuming that they manage physical memory, the page table registers, the user kernel bit, interrupts, all of those things, right? So the crux of this problem is that the kernels of these guest operating systems, they need to be able to act like kernels with all of the power that entails, all of the power and all of the privilege. But we also only want them to be able to act like a kernel within their own operating system, right? I don't want the guest operating system on the left to screw up the guest operating system on the right, all right? So what we need here is a solution sort of very similar to what you saw before. We need something to interpose between these operating systems and physical hardware. And in the world of virtual machines, that thing is called a virtual machine monitor, or a VMM, right? So I will usually say it VMM because who has the time to say virtual machine monitor, all right? The VMM is gonna run on the hardware, right on top of the hardware in kernel mode with the guest operating systems in user mode, all right? And the VMM is gonna virtualize the computer to the guest operating systems, all right? So we could think about we could think about a design where, okay, every single instruction from the guest operating systems sort of passes through the VMM, right? And the VMM does something, maybe it makes some changes, maybe it just sort of passes them through directly to hardware. This can be done. In practice, it's very slow, right? So to get this to work, we want to think kind of carefully about, when is the VMM involved, right? It's going to be involved with the privileged instructions, all right? So we'll think about how to deal with that. Right, the VMM, it does have a bigger job here. It's also, it's in the business of allocating resources between these guest operating systems. It has to dispatch events. So if there are, forwarding interrupts back and forth between guest operating systems and hardwares. But the thing we're really going to care about today is how it deals with instructions from the guest operating system that require some interaction with the physical hardware. So how the VMM helps these virtual machines run privileged instructions. Right? So we're only going to go through 2 examples. We could spend probably like 2 solid weeks on virtual machines. We're not. We're going to spend roughly half to 2/3 of one lecture. All right, so I'm going to give you two examples, but overall, we see virtual machines follow the same sort of idea. All right, and so part one of that idea, our guest operating systems are going to be running in user mode, all right? Which of course is going to cause problems. It's going to cause problems when any sort of privileged instruction needs to execute, right? Because those are things that need to be run by something with like kernel level privileges, right? So the way these systems work, these privileged instructions are going to cause an exception because it can't be run, right? The VMM is going to intercept them, which in this context we call trap, and it's going to emulate them, right? So this overall approach is called trap and emulate, right? Now, the very first question, like the first question that I would have if I were you, well, maybe you have a different question, is so basically, what does this mean? What does it mean to emulate an instruction, right? What does that look like? Like, it'd be very easy if I just put the word on the slide and then we just moved on, right? You need to understand though what it might mean to emulate something. All right, so like I said, we're gonna go through two examples that will illustrate some of the nuances, some of the complexities that a VMM has to deal with. All right, this isn't absolutely everything that they have to do. This is two key issues, right? So to look at this first question, to think about like, well, what does it mean to emulate something? We're going to do a specific example, right? We're going to talk about virtualizing memory again, right? And so we'll start to make this a little bit more detailed, right? We're going to be interested in sort of exactly what's going on in these guest operating systems, right? They have their own user kernel bit, they have page tables, they have page table registers, right? And so what's the problem of virtualizing memory in this context? You already know everything about virtual memory, right? What more could there be to say, right? Well, notice we have more levels than we did before, more layers in this system, right? So if we're thinking about, virtual memory just within one of these guest operating systems, we have a notion of virtual addresses going to physical addresses. You've seen that, right? I'll start making those names a little bit more precise so we can distinguish between what's going on in our guest operating systems versus on our hardware. So that virtual memory system would, be kind of contained in that single operating system, right? Go from a guest virtual address to a guest physical address. But we need to go a level deeper, right? We're going to want to translate all the way down to, well, what's the actual hardware, right? And I'm going to use the term host here again to think about like a host system with guests running on it. All right, and kind of the big question is, well, in this physical hardware, the bottommost layer here, what is that page table register going to point to, right? What page table is the hardware going to use, right? So how does this work in a virtual machine? So there's two ways to do it. I'll show you one way and then the other way. Okay, I'm going to show you the older way first. All right, so we're going to keep this picture. I'm going to make it a little bit bigger because I need some more space to kind of put some more stuff in here. Right, so we're still talking about virtual memory. All right, oh yes. And this example, so what does it mean to emulate? In this example, our VMM is going to need to step in and translate. Right, it's going to need to help us get from guest physical addresses to host physical addresses. All right, so emulating an instruction, it's going to depend on what the instruction is. All right, so let's see it in action in this one. All right, so again, same picture, it's a little bit bigger. The things that I really care about for virtual memory are things like page tables. All right, so I definitely care about those page tables there in the operating system. And I care about page table registers. All right, within a guest OS, there's a page table register there, but then there's of course the page table register that actually lives in hardware. All right, so our question is kind of, well, what does that point to? All right, so we're gonna have a couple of things to keep track of here. I'm going to start writing them on the side. So right now this box looks like it's floating in space. There's going to be other boxes to float with us. This is just a reminder that within a guest OS, we are going from virtual to physical addresses, but we're staying within that guest operating system. We haven't gotten all the way to the translation that we need. All right, so how does this work? How does the VMM step in? Right, what instruction is it trapping? How does it get the information that it needs and what does it do? Okay. Here's what happens. All right, so first of all, the guest operating system is going to go to load its page table register. This is immediately going to trigger an exception guest operating system is running in user mode. This is an instruction that requires kernel mode, right? So an exception is gonna say, hey, you can't do that. The VMM is gonna intercept that, it's gonna trap, all right? So it's trapped that instruction, and now it has to decide what to do, right? So the first thing it's gonna do, it's gonna locate that guest OS page table. It's gonna bring it into its, deal with it on its own. It can do this, right? It can do this because the address of that table is part of the load call, right? So it knows where this table is. It can look at this table. What it's going to do with that, it's going to combine that guest OS page table, that page table there in blue, with its own page table, right? So the VMM is going to keep its own page table, right? That page table is going to map guest physical addresses to host physical addresses. So we now have two tables here, right? I can go from a guest virtual address to a guest physical address. Then I could take that guest physical address, look it up in the ping table, and get a host physical address, right? So the VMM is going to be responsible for keeping this ping page table up to date, right? And what it's going to do, you can see I've put a little addition sign there. It's going to take this blue page table, combine it with the pink page table. It's going to make a purple page table, right? And that final page table, it does the full translation, right? So it gets us, instead of going guest virtual to guest physical, then looking that up, going to host physical, it just gives us, right? It gives us that full lookup as one. And that is what the host hardware is going to use, right? So basically what the VMM did is step in here and said, hey, guest operating system is trying to load its page table, right? And it can't do that, right? Because it is a user level thing. It's trying to run a privileged instruction. That's going to cause an exception. I'm going to intercept that. The virtual machine monitor, I have my own page table set up. I'm going to help this translation along. I'm going to make this page table for the hardware. The hardware can go on and use that. No one's the wiser, right? So the VMM has stepped in here and helped, right? Now, there is an interesting question, right? I sort of gave you this VMM page table just kind of out of thin air, right? It's there, the VMM has it, you don't have to worry about it, it's chill, it's fine, right? But, certainly the VMM has to be kind of keeping this table up to date, right? Mappings can change, it's got to sort of be tracking, what the guest OS is doing with its own page tables, right? And the challenge here with that, it's, you can imagine, okay, well, all right, in this setup, the VMM, it can intercept those instructions, right? Trap them, do the updates it needs to its page table, and then kind of go on about its way, right? One of the challenges, though, and this is actually leading us into the second question we're gonna ask about virtual machines. One of the challenges is that a lot of the updates that a guest OS might do to its own page table don't automatically throw an exception, right? They don't not all of them need to be run in kernel mode. So this presents us with a problem, right? There are some instructions here that might cause the VMM maybe not to step in and change things, but to update its own sort of data structures, right? So how is it going to do that? How is it maybe going to force some sort of trapping mechanism to kick in, right? In this case, one way we could do that would be to take the guest operating system's page table and have the VMM just mark it as read-only memory, right? We can do that. Then if the guest operating system tries to modify this, the hardware, again, is going to trigger a page fault. It's going to say, hey, you're not allowed to do this. That'll get handled by the VMM. The VMM can update its page table, right? Its ping page table here, and then resume the guest operating system, all right? So the moral of the story here, in many ways, right, this idea of trapping and emulating, that is the high level idea of how this is going to work, right? We're going to see a second example in a second. That's a high level idea, but there are a lot of subtleties. Exactly how a VMM emulates a particular instruction depends on what the instruction is doing, right? This is how we would deal with a guest operating system loading a page table, right? The process is going to look totally different when we talk about emulating anything to do with like the user kernel bit. It's just a whole different job, right? Trapping is also, there are some complexities there, right? We have to make sure that all of the instructions that the VMM needs to trap can be trapped, all right? Now, I told you there were two different ways to deal with virtual memory, all right? This is one way to deal with this, usually known as shadow page tables. The second technique, the more modern way. Most modern hardware comes with support for this type of virtualization. We'll discuss that in more depth in a second. Right? And for virtualizing memory specifically, the physical hardware basically knows about both of these tables, right? It does the lookup, it does the translation on its own, right? So rather than the virtual machine monitor having to build that final third page table, the hardware can basically just look up in the guest OS page table, use the result as a lookup into the VMM page table, and go on about its way. All right. So this is what virtual memory looks like in a VMM, right? It's very high level explanation, right? We're not going to get into a ton of detail, but notice that you're seeing virtualization applied again. The guest operating systems, they don't need to know anything about this process, right? They're just running as they were before. They think they have access to all of the hardware. Of course they don't, right? And notice that we have something here that's interposing. It's taking care of all of those details, right? If you imagine back in the day, two weeks ago or so, 3 weeks ago, when we talked about virtual memory the first time, right? The programs, they don't have to worry about all of the mappings, right? The kernel took care of that, right? So similar things here, right? So back to our general idea, trapping and emulating, right? Let's think about another example, right? Our second example is going to deal with virtualizing the UK bit, this user kernel bit, and it's going to lead us into the second question. Right? And I touched on this before. What about when our VMM has to emulate an instruction that doesn't trigger an exception? When there's an exception, it's easy for the VMM to step in. It says, exception, my time to shine, trap it, do something, right? Trap it and emulate it, right? But just like that example with virtual memory, sometimes the VMM needs to react to an instruction that doesn't cause an exception. All right. And so this is going to come up in particular with when we think about how to virtualize the user kernel bit. Right now, you might look at this and say, "Oh, it's one bit. This should be so easy, right? It should be fine, right?" We could have, say, the VMM just store the current state of the guest OS's UK bit, right? Store one for each guest OS, not a big deal, just a couple bits, right? Privileged instruction in the guest code will cause an exception. The VMM can trap, it can emulate it, like it can just go about its business, and maybe it just keeps its own copy of a UK bit, just the same way it kept its own page table, right? The problem here is that instructions that don't cause an exception, right? And the UK bit is involved in two of those, right? So remember, the UK bit is the bit that tells us whether we are running in user mode or kernel mode, right? On some architectures, anyone, user or kernel, is allowed to read the current bit, right? So you can imagine, right? You can imagine a guest operating system reading it and sort of observing that it's running in user mode, and maybe it's expecting kernel mode. That you can imagine the confusion that might cause in an operating system, right? There's also anyone typically is allowed to switch the user kernel bit to user, right? In that case, one of the things that VMM might need to do if we're switching into user mode is replace its shadow page table, right? Replace that pink page table, right? So again, there are these issues of what happens when the VMM needs to do something, right? But it can't trap the instruction by default. Virtual memory, we said, well, okay, we're going to mark some memory as read-only, right? So that it causes an exception. Right. Well, there are a few maybe like higher level solutions to this problem. I'm going to give them to you in order from worst to best. All right. Worst solution is known as paravirtualization, which is that's a very, very fancy name. Practice very hard to be able to say that on the first try. In paravirtualization, we modify the guest operating system slightly to account for some of those differences. And the reason that I am personally ranking it as the worst, like this is my ranking. It compromises our original goal, right? Our original goal was compatibility. I don't want to have to modify the guest operating systems. Like that's not what I'm about here, right? For some operating systems, that's also really hard to do. You can make these changes in a Linux kernel. You can really make them to Windows without Microsoft's help, right? So this is not a solution that is super exciting for us, right? Another idea known as binary translation. right? With binary translation, VMM is going to look at code from the guest VM and sort of replace problematic instructions with an instruction that traps, right? That's sort of like what we saw with virtual memory. And then once we can generate the trap, the VMM can intercept the instruction and emulate the desired behavior, right? It's going to force traps. It's going to force exceptions where it needs them to happen, right? This is not a bad solution, all right? Some virtual machines used to work this way, right? But arguably the best of the three, at least these days, is to provide hardware support for this, right? Some architectures have virtualization just built into their CPUs, right? And the way that this looks is they basically come with like a special VMM operating mode, right? So instead of just having users and kernels, right, we sort of have users and kernels and VMMs. Things like the true level of page tables are just implemented in hardware. And this hardware support, it makes the VMM's job easier, right? It lets the guest OS manipulate the UK bit and manipulate the page table under certain conditions. It's very flexible. It lets the VMM kind of choose which interrupts it wants to handle. Most modern VMMs take this approach, right? And one thing you can see from this, you've seen it in almost every operating system lecture, right? You've seen that underneath whatever we're trying to do in an operating system, to get it to work fully, we need some amount of hardware support, right? Like we needed like an atomic exchange operation in hardware. We needed to disable certain types of interrupts in threads. We needed the memory management unit and like hard-coded addresses of the page version. Like we needed all of these things, right? Similar here, we have hardware support underneath to let this happen, right? So this is our very, oh, Henry's doing some Inception style question on us in the chat. Great thing to ponder. So this is our sort of high level, pretty fast introduction to virtual machines. All right. What you should be getting from this is that that application of virtualization that you've seen within an operating system, we can zoom out. Right? We can apply the same principles in other ways. And again, this is a very common computing environment these days, not just on your own personal laptops. It's very nice to have access to multiple operating systems, right? But in things like a data center, this is really, really common, right? So thinking again about, why we did this, right? What we were dealing with here. We were thinking about, okay, I want to be able to run multiple operating systems, the same physical hardware, because that is a very cool thing to do. But I've got to figure out how to share the hardware easily. And I've also got to deal with bugs in the kernel. All right. Now, all up until this point in this class, we haven't really talked about bugs in the kernel. Like I kind of presented the kernel as like this, like immaculate thing to you, right? It's doing its job. It's perfect, right? This is not true, right? There are tons of bugs, right? There are plenty of bugs inside a kernel, right? And yeah, okay, we can think about how to protect multiple operating systems running alongside each other from those bugs. But what about the operating system itself? I don't want my operating system to crash, right? That's terrible. It's worth taking a few minutes to think about why might there be bugs in the kernel, all right? Why might there be bugs in the kernel? Many operating system kernels look like this. All right, Linux looks like this. Linux is effectively one really big C program. Despite all of this talk about enforcing modularity, which Linux does just a wonderful job between user programs, between the kernel and user programs, there's very little modularity within the kernel itself. All right, there's a lot of really, really careful software engineering. I do not want you to think that like Linux developers just kind of throw some code and they're like, yes, it works. No, very careful software engineering, object-oriented programming, common interfaces between components, all of those good things, right? But it's very complex. It is what we call a monolithic kernel, right? This means that ultimately a bug in this kernel can bring down the entire system, right? And so, maybe that's just how kernels look. But in fact, there is a competing design, all right? In contrast to a monolithic kernel, there's something known as a microkernel. Right? Microkernels attempt to enforce modularity by putting different types of subsystems in user programs. right? The exact subsystems that might go there, that would, that would depend a lot on your design. But you can imagine like file servers, graphics, networking, like these are just kind of user level programs, right? There's still probably going to be bugs. There's bugs in all code, right? Nobody writes perfect code all the time, right? But in theory, we should get some of the benefits of modularity, right? We'd hope that there would be fewer bugs because the system, it's more modular. It's not one big program. It's like a lot of medium-sized C programs. We would hope that, a single bug would just crash that particular module, not the entire system, right? Like, you would sort of look at this type of system and say, well, that looks like a lot more appealing from sort of an O33 design standpoint. But I told you that Linux looks like the thing on the left, right? It's this monolithic kernel. Why, right? Why is it like that? Okay, there are a few reasons. You can decide for yourself if any of these reasons are good reasons, right? I'm just going to give you some possible reasons. One, communication costs in a microkernel are high, right? It is higher to communicate between these, or it takes longer to communicate between these modules than it does to make a single procedure call. You can almost imagine like when we took the very extreme view of enforcing modularity, putting a client on one machine and a server on another machine. We haven't really talked about this yet, but even if the network is working perfectly, now it just takes longer for a request and a response to get back. So that's one issue. So a performance issue is a huge thing. The second thing, it's not always clear that moving certain components to user space is really a win. For instance, if I pull, say, the file system out into one of these blue boxes, I have the file system as this nice little module, and it crashes, right? What good is your operating system if the file system isn't working, right? If it's not, say, saving data or something like that, right? All of these things are so important. It's not clear that the system can really kind of work around a crash there. There's also, redesigning a system to work as a microkernel, it's complicated, it's difficult, right? There are a lot of different design choices we'd have to make. And there's definitely a trade-off between, say, spending a year of developer time just rewriting the same operating system in a different way or adding new features. All right, so those are three reasons. There are a lot of other reasons. I'll put some additional reasons in the notes so that you can think about them. All right, there are parts of Linux that have microkernel design aspects to them, like some USB drivers, printing SQL databases, all of these things. You can restart those components without crashing the whole kernel or crashing other programs. Right, but it is kind of interesting to think about, like, well, the design of within the kernel of an operating system, it's not always that modular, and it does cause problems, right? It causes there to be bugs, right? Now, since one of the reasons I mentioned here was dealing with communication costs, right? I want to focus in a little bit on that because that's going to lead us into the next part of O33, all right? In part because we're talking about performance here. The third point was that in the chat, the third point is that there's a trade-off between dealing with developer time in rewriting a kernel to do the same thing but be designed differently under the hood versus adding new features, right? So, and you can take either side of that. You can say, well, I do think that's worth it, right? But that is a reason, right? But so let's talk about performance a little bit. We have 9 minutes. We're going to spend 9 minutes on performance, but performance really comes up all of the time. All right. So you have seen performance come up in almost everything in this class so far, specifically in the world of operating systems, right? Think about all of the performance issues we encountered. We cared about the time it takes to access a piece of memory, right? Remember when we talked about page tables having to be allocated contiguously, right? That was so that the hardware could do a fast lookup, right? We also talked about the trade-off of balancing that access speed against storage when we were talking about hierarchical page tables, right? And of course, when you're thinking about memory access, you can think about caching, right? If there's a particular byte of memory that my system is reading over and over and over and over, put it in the place that is fastest to access, right? Put it in your smallest, fastest cache, right? We talked about concurrency, right? When we talked about locks, we talked about how coarse-grained locking often gives us a correctly working system, but a slow one, right? Remember the example where Howie and I were both trying to move a file, two different files between two totally different directories, but we had to do it one after the other because we had this lock that was protecting everything about the file system, right? It was a correctly working system, but it was going to be very, very slow, right? If we can safely execute multiple actions at once, we should, right? And that came up when we talked about yield. We talked about how yielding makes especially good sense when a program is waiting to do something, right? Especially if the thing it's waiting for is for another program or another thread to take some action, right? Zooming out, you've seen performance in other places as well. When you talked about DNS, right? DNS includes caches, it has recursive queries, it lets you query any name server to start, not just the root server. All of those things, they keep the root server from being a bottleneck, right? Keep the root server from kind of pegging the performance of the system. They let us exploit the fact that many people are looking up the same name, right? So given all of this, given you've seen so much about operating systems at this point, right? We can start to talk about performance in a more general sense, right? We will continue to talk about performance for the rest of this class. So like, how do we measure it? What should we expect from it? How do we improve performance? When do these apply? All right, so we're going to talk briefly about sort of some common performance metrics. And these, again, they're things you've seen throughout, but this is a great point into the class to kind of bring them together so that we can think about applying them to the next part of the class. All right, so two really common metrics in systems. First is latency, right? The amount of time it takes to complete a single request. Right, we can talk about, say, the latency of a particular memory access, right? How long does it take to read a particular piece of data? When we start talking about networks, we can talk about latency in a network. How long does it take a request, say, to get from the client to the server and maybe even be processed by the server and get a response back? And we could talk about latency. Alongside latency, we'll often talk about throughput, right? How many requests over a particular unit of time can we do, right? How many reads or writes can I do to a disk at once, or say within a minute, or within a second, or a nanosecond, right? How fast is my network? How much data can I send over a particular link? That's something that's coming up for us, right? Sometimes, these quantities are not unrelated, right? For instance, if I'm dealing with just like, say, a single CPU that is, executing requests just one by one, if one request takes 1/10 of a second, then that CPU can handle 10 requests per second, right? But the minute I add any sort of concurrency or any sort of parallelism, all right, we can increase things. And so even though, these quantities may show up in lots of different places, right? You could talk about latency of a disk, you could talk about latency of a network, you could talk about them all over the place. We see similar patterns. All right, so think about a system. Think about Katrina's amazing web suite. Okay, remember llamas. We're buying llamas, and now we've made it through operating systems. We're 5 minutes away from being masters of operating systems. Surely we can think about adding more clients into our amazing web suite. All right. So at the beginning, I start the web suite running. I'm going to let you all be clients today, so you can think about you think about buying your own llama. All right. A few of you show up. All right. I have a lot of resources in my system. I can handle all of your requests. Latency is very low. It is not taking me a long time to handle your requests. All right. Throughput is also low because I'm not getting very many requests, right? If only like 5 of you are trying to buy a llama each day, well, I'm selling 5 llamas a day. All right. But eventually, Katrina's amazing web suite catches on, right? Start to get more requests, right? This is what we will see happen typically to these quantities, right? Throughput will start to go up. I'm getting more users, I'm dealing with more requests until I'm pretty much maxed out. I'm using all of my resources as fast as I can. Throughput cannot increase anymore. There is a limit, right? Latency typically remains low until the system starts to be so heavily utilized that people have to wait. All right. If you don't like the llama analogy, which would be wild, because how could you not? You can think about like going to a grocery store, right? There's lots of checkout lines. When it's not crowded in a grocery store, it's no problem. You get in line and bam, you're in and checkout right away. But once you have enough people that all of those checkouts are full all of the time, now you have to wait, right? Now latency is starting to increase. In theory, you could be waiting forever and ever, right? So what do you do with this? What are you meant to do with this idea as system designers, right? How does this help you, right? Well, we're all engineers on Katrina's amazing web suite, and people are complaining to us that it's taking too long to buy a llama, right? What would we do, right? The first thing we'd want to do is compare, okay, well, what are users seeing? Like, what's latency like? What's throughput like? And how does it compare to what it's supposed to be, right? If I tell you that users of Katrina's amazing web suite are able to buy 100 llamas a day, is this good? Is this bad? It depends, right? So we can think about utilization, right? What fraction of our resources are being utilized, right? And you could think about it in operating systems. How fast is that disk reading or writing compared to how fast it can read, right? So we would start to measure different components of our system, right? Ideally, we would come to discover some sort of bottleneck in our system, right? The piece that's limiting performance, right? And say, we say, okay, we've got all of these clients, they're getting the requests in, but I'm finding that the queue that serves these requests in front of the server, it's building up, it's just not working, right? So once we find that, how would you fix it, right? And this is also something you'll start thinking about in your design projects, right? When you start to think about performance, how do you address performance, right? So we have some ideas. We have these systems level techniques. Some of them you've seen, right? If you add a cache, if some sort of access is slow, maybe we can run certain things concurrently, right? One that you haven't seen as much of, maybe we can batch requests, right? To eliminate some startup costs of certain requests. So all of those techniques, the things that they have in common is that they kind of operate at this systems level, right? They're not things like make this algorithm faster, like take it from n squared down to n log n, right? They're more systems level techniques, but they also can't just be thrown in anywhere. You can't just put a cache anywhere in your system and assume that latency will decrease, right? Caching only makes sense if there's a pattern of retrieval that you can exploit. Okay, so you have seen examples of all of these. You will continue to see examples of all of these. We'll even give you some additional examples that you can think about in the context of your design project. But this is kind of just a good point. Like I said, you've seen so much about operating systems. You've seen all of these performance issues come up. This is how we start to think about this as a more unified look at performance. Right, so we'll talk a lot more about latency and about throughput as we move on to networks. But today is the end of operating systems. Karen, how do you feel about the end of operating systems and moving on to networks? How many thumbs up would you give that? 2 thumbs like this high up, yes. So this is very exciting for, for a lot of us, all right? You've seen a lot about operating systems and you've seen a lot about performance. And now you're kind of on the precipice of being able to build these bigger systems. You've got one machine working, all right? So now we're gonna start kind of going back to our client server type systems, our DNS type systems. We're gonna spend the next few lectures talking about really the network in between things, how it works, how it fails at times, and then we'll be able to move on to these really big systems. So yeah, come back tomorrow because today is Tuesday, which is very weird. Come back tomorrow for my favorite lecture of the year, I would say. But that's the end of operating systems. Congratulations, students, for being operating systems masters. So I'll hang out for 4 minutes if there's questions, but if not, I'll see you all tomorrow. And I'm gonna stop recording.